coming and welcome to the WMISA 2024 AGM and seminar for the year. I'd like to start out by acknowledging the traditional custodians of country and their connections to land, sea, and community. We acknowledge and we pay our respects to elders past and present. I'd like to now pass over to Melanie Finch to introduce our speaker for today, and I'll jump back in at the end of the seminar to kick off the AGM. So on to you, Mel.
Great, thanks, Erin. Yes, it's great to be with everyone today. This AGM is always such an exciting event in the WMISA calendar, so thanks for coming along. Feel really lucky to have Rebecca Carey with us today. So Rebecca's research contributes to the knowledge and understanding of volcano-sedimentary processes and products, as well as marine geoscience. So research combines volcanology, sedimentology, geochemistry, petrology, marine geology, and economic geology. So many of you know that Rebecca just got awarded a future fellowship, which is super exciting. That will be commencing soon, and she's had other ARC funded projects as well, and projects tend to focus on investigating the spatio-temporal relationships among plumes, plate boundaries and eruption products in the offshore Eastern Australian context, and exploring complexities in the volcanic architectures in modern and ancient settings. So that all sounds really interesting and exciting, so I'm looking forward to hearing more about that today. So Rebecca, I'll hand over to you to begin your seminar. Thanks so much.
Okay, thanks. Thanks very much, Melanie and Erin and Alanis for organising this AGM seminar today. So when Melanie contacted me to give this seminar, I wasn't in a very resilient framework or frame of mind, really. And so I put Melanie's invitation off for days, was it, Melanie? Maybe a week, because I just didn't know if I could commit to a seminar. But as I gave it a bit more thought and a few more prompts from Melanie, I decided that, yes, I did have something to contribute. So let's have a go at that. And my first thought was, well, let's just talk about science. Science is safe. I know my science. I can deliver that well. And then I jumped onto the WMISA website, where all the YouTube recordings are shelved, and caught up on a few of the talks from 2023 and 2022 that I missed. And in viewing those, I just want to say a big thank you to those speakers who have had the courage and for being brave to really talk about their career paths, their challenges, some of the barriers that they're experiencing to success in their lives and their careers. That really gave me a bit of a push, actually, to think about, well, can I contribute something else that is along those lines, but has that of my career over at least the last decade. So I'll talk a little bit about that at the end. Okay, so the presentation today, I'll just hide those meeting controls. There we go. So the presentation today is called Pop, Fizzle, Bang, Case Studies of the Interactions of Volcanoes and the Magma with the Ocean. I'll hide those again. There we go. Okay, so I thought I'd just start off talking about my career path. And in some ways, my career path's been very ideal for me and my family, and I'll just walk you through all of that. So I did my PhD at the University of Hawaii, and during that time I was based in Hawaii, which was wonderful, but my field area was in Iceland, which for a volcanologist is also equally as wonderful. So I had two PhD supervisors, one in Hawaii and one in Iceland, and I completed my PhD in 2009. So in 2009, I had a small break from academic work, and I was working on a project for a disaster centre in Hawaii, putting together a short course for emergency response personnel and community organisers to deal with volcanic hazards. And so that was a kind of a nice little transition into applying some of my fundamental scientific knowledge into a product, a short course, that would actually have societal benefit. I then transitioned into my first postdoctoral research associate position. So that was at the University of Berkeley. Now, when I was in Hawaii, the Kilauea volcano wasn't erupting. It wasn't erupting explosively. It was just erupting effusively. But as soon as I got to Berkeley and landed there, Kilauea did start to erupt. So I ended up doing some work on Kilauea and those 2008 to 2011 eruptions from Berkeley, but with some fieldwork in Hawaii, which was kind of ironic. And then at the end of that time in Berkeley, I worked with Jocelyn McPhee and Sharon Allen to put together an ARC postdoctoral research fellowship proposal to apply what we'd learned about submarine eruption processes terrestrially and apply that to the submarine setting where we know things have to be different because eruption into water is different from air, and the seafloor is at significant hydrostatic or confining pressure. So I completed that postdoc at University of Tasmania, and at the end of that postdoc, I was probably 2 weeks before being unemployed. And I didn't really have a backup. I did have a backup, but it's kind of secret, and I've only told a few close friends. But it was a backup outside of academia. So at that time, I was considering about working for industry in Tasmania in sort of the mining industry, just so that I could do geology. About 2 weeks before that, sort of before the end, I was lucky enough to get my continuing position at level C at the University of Tasmania. And I also got my ARC DECRA proposal funded. So I went from essentially looking at a future with nothing to having two things at the same time. And so the University of Tasmania, I went on to my DECRA, and the University of Tasmania backfilled my position with another postdoc. And so it wasn't until after I'd got my continuing position in my DECRA that I had my first child, Eva. And that was, truthfully, it was on purpose. I didn't feel like, me personally, I didn't feel comfortable having a child until I had a full-time position in work that I enjoyed. And when I finished my DECRA, I went on to my level C position, had my second child, Micah, and then I was applied for a promotion in 2021 to level D, and then in 2024, that little bubble's moved. That in 2024, I got the Future Fellowship. So that's kind of my career progress. But these arrows in red up the top here, when I was putting this together, I was thinking about how tortuous that pathway was, and the things that happened and the people that I met and who mentored me through that process. And here are 7 people that mentored me. So that each arrow is a person, and those are 7 people that mentored me through that process. And it wouldn't have been so, it wouldn't have been such a straight pathway had it not been for those people. And so it's been a combination of mentorship, a lot of luck, to be honest, a lot of luck, being at the right place at the right time, some hard work, but also this fourth component I was thinking of, it's actually being a decent person that people want to work with. So being kind and not being an idiot. So I just keep going. Okay, so I just thought I'd show a few happy snaps of me and my life as a terrestrial volcanologist. So the reason I got into volcanology was that I did my 3rd year of my bachelor's degree in Hawaii, and I didn't have any money because the Australian dollar was worth half of the American dollar. So I worked for a professor of volcanology, and I did all of his laboratory work for his 5 PhD students. I also coordinated the field trips to Kilauea volcano. So having done all that, I knew that I wanted to be a volcanologist, and so off I went. Okay, and one of the reasons why I became a volcanologist was just because eruptions on land are absolutely spectacular events. And so this is a photo of the 11th of September 2020 eruption of La Palma in the Canary Islands. And what we can see here is some explosive fire fountaining that's producing pyroclasts that are being pushed into the atmosphere. And those fire fountains are probably just a few hundreds of meters high. There's an eruption column and plume here in this grey area here in the atmosphere. And then there are lava flows which are travelling downslope and into the lower topography regions. So here's just a little bit of background. So explosive eruptions are driven by the dissolved volatiles that are within magmas at depth, the magma viscosity, and the rates and timing by which those volatiles exsolve and are transported in that melt phase. So for explosive eruptions, the model is such that as magma is decompressing, as it's rising towards the surface of the Earth, the solubility of those dissolved volatiles, such as CO2 and water, decreases. So those volatile phases become unstable, and so they exsolve into bubbles. Now, the material in those bubbles is actually a supercritical, for water at least, is a supercritical fluid. And so it's kind of like a dense gas. Now, those bubbles are buoyant relative to the melt phase in which they're traveling. And if magmas are viscous enough, if they're sticky enough, then those bubbles can couple to the magma, and the mixture of the bubbles and the magma ascend together. Now, dissolved, those bubbles are buoyant, as I said, but they're actively expanding during that decompression phase. Now, the conduit has a certain volume, the pipe to the surface. And so if you're expanding this melt bubble mixture in the same volume, it has to go faster. So it accelerates to the surface, and the magma goes through what we call brittle fragmentation. So that's how we create explosive eruptions on the Earth's surface. Now, if magmas have a lower viscosity, which means they're more fluid, then those bubbles nucleate and they grow, but they can decouple from the melt phase. And they decouple and they form these permeable pathways, and the gas phase, which is the energy driving magma ascent, is essentially lost to the country rock, the conduit walls. And so in those cases, we expect that magmas will erupt as lavas. So this is what we know principally from observations and being able to sample these products on the Earth's surface. But we know that it's likely to be different in the submarine setting because for every 10 meters of water depth, the water pressure increases by a bar. So at a kilometre, it's going to be 100 bars of pressure or 1 or 10 megapascals. And so styrofoam cups at 10 meters are going to retain their shape and size. But when we push them down to the bottom of the ocean, they become maybe a tenth of the size. And so that's just the effect of the confining pressure, the weight of the overlying water column. So I just want to show this one graph because it's from Ray Kaz's new reference volume in volcanology, but it kind of highlights this bubble expansion process really well. So on the y-axis, we've got specific volume of water, and on the x-axis, we've got pressure. So a magma at a certain temperature, 800, 900, and 1,000 degrees. Well, sorry, not magma, water. Yeah. So water at those temperatures at 120 megapascals of pressure essentially don't have much volume as a supercritical fluid. And that's because it's a really dense gas. But you'll see that as that supercritical fluid decompresses to lower and lower pressure, that supercritical fluid is allowed to expand. Now, at very low pressure, so less than 20 megapascals, when we're actually not in the supercritical regime, we're in the steam regime, that gas phase can expand significantly, almost exponentially. And so what this means is that for volcanoes that are sitting on the ocean floor at significant depth, maybe 40 megapascals, which is about 4 kilometres, when bubbles do exsolve, they can't expand. And so they're not providing that expansion energy to couple with the magma to drive magma magmas and accelerate them to the surface. Whereas at volcanoes that are in shallow water depths, so maybe less than a kilometre or so, when that exolved volatile phase is created, it can expand hugely, and that helps to accelerate the magma, which then helps to break the magma apart at a critical threshold. So we know all the theory, and the issue has been in the submarine setting is that until 2006, we'd never seen a submarine eruption. And so everything we knew up until 2006 had been derived from very careful and detailed field observations of submarine volcanic and volcano-sedimentary successions that had been uplifted. And so these are beautiful, like in Australia, across the Macquarie Arc, in Tasmania, in Western Australia from the Archean, Greenland, Canada, all over the place, Japan especially. And so all of the advances in understanding submarine eruption processes was very incremental and required a significant amount of observational field work to be able to be comfortable to describe a process. Now, in 2006, that all changed because one of the remotely operated vehicles that was working in the Marianas Arc in the Pacific serendipitously came across a volcanic eruption taking place. So I'll just show that video. So this is the northwest rotor, and what you can see is a small volcanic cone that's about 10 meters in diameter. So that distance there, and gas bubbles with molten red magma around them are ascending in a conduit, presumably. And when that material gets to the ocean surface, those bubbles are collapsing or fragmenting and forming and quenching and forming this pyroclast mixture. So if you go on to NOAA's website, maybe I'll if you just Google Northwest Rotor on the NOAA website, you can actually get this video with all the audio, and the audio is spectacular. Like the people in the who are observing this are just like can't believe what's happening. So this was the first observation in 2006, and this eruption, the products were sampled, and this eruption really kind of was a step change in how we understand explosive eruptions on the seafloor. This was about 600 meters below sea level. Okay, so in this talk, there are lots of submarine volcanoes and seamounts. There's a recent paper in 2023, I think, that have found over 40,000 seamounts with satellite gravity. But these are the reported submarine eruptions where we've got evidence of seeing the eruption or acoustic signals which are related to bubble bursting of volcanic lavas and or explosive eruptions. And so the three case studies I'll provide today, the POP is from West Marta in the Lau Basin in Tonga. The Fizzle is the Kermadec Arc volcano called Havra, and the Bang is, of course, the 2022 eruption of Tonga, of Hunga volcano in Tonga. Okay, so West Marta in 2009 was also another serendipitous discovery of an eruption taking place while people were doing work in the region. So West Marta sits in the transition between the Tonga Arc and the Lau Basin, just up there. And this is what they saw from the remotely operated vehicle. And so what you can see again are these gas bursts or slugs that are surrounded by incandescent magma, and these gas slugs are getting into the ocean, and that magma around those gas slugs is quenching and forming pyroclasts. Now, at the same time that those explosive eruptions are happening, just there, you can see that there's also lava forming down and flowing down the side of the little volcanic cone at West Marta. Okay. So this was another event where it's fundamentally changed how we understand, in this case, more mafic explosive submarine eruptions. And at this eruption depth was about 1,100 to 1,300 meters below sea level, so significantly deeper. Okay. So one of my PhD students went on Yeah. One of my PhD students went on to do a postdoc with Ryan Portner at San Jose State and analysed all of this video footage in detail, and was able to demonstrate that unlike subaerial environments where it's actually bubble expansion and the breakage of that bubble that forms the pyroclasts, in this deep submarine setting, what's actually happening is the magmatic volatiles, the gas that's in this bubble, is condensing. And so these pyroclasts are being formed by implosion rather than explosion. And so that was one really significant output of this eruption that really fundamentally changed our understanding. Just like that again. Okay. So now I want to go on to the Fizzle, the Havre 2012 eruption in the Kermadec Arc. So this is North Island of New Zealand, and the Kermadec Arc is this volcanic arc defined by those white triangles, stretches up to the Tonga Arc, and Havre volcano sits sort of mid Kermadec Arc. So it's a large, very mature stratovolcano that has a 4 by 5 kilometre large caldera on its summit. We don't know when the caldera formed. But in 2012, a woman was travelling from the Pacific to Auckland, and she looked out of her window and she could see this area of aqua blue aqua blue type coloured water. And so when she didn't know what it was, whether it was an oil slick or a pumice raft or something else. And so when she got to Auckland, she got in contact with GNS Science in New Zealand and said, oh, I think I've seen an oil slick or a pumice raft, and it was approximately this duration into the flight. And so that triggered a look through the NASA MODIS satellite imagery to find out exactly what it was. And this is the first image that we have of it. And so what you can see here is that there's a plume in the atmosphere that's extending from a point source. We've got this grey area here, which is a pumice raft. And then in the water column, we've got these aqua regions, which are related to pumice accumulations in the water column. So through the NASA satellite imagery, we were able to demonstrate that there was about 21 hours of pumice raft formation. We estimated the volume of the raft to be about 1.2 cubic kilometres, so about 750 times the volume of the MCG. And because we've got volume and duration, it's about a 10 to the 7 kilogram per second eruption. So it's kind of an eruption that would happen terrestrially, maybe 4 to 5 times every 100 years. Yeah, just for comparison. So based on this satellite imagery and the work that we did, the team I was working with were very excited, because automatically you think about pumice, you think this is an explosive eruption. We knew it was from Havre, and we knew that the depth of the summit of Havre was 900 metres below sea level. Now, this pumice washed up onto the eastern Australian shores. You can pretty much still find it in the sand dunes. And so we also knew that it was a rhyolitic eruption, because those pumice components were about 78% silica. So we published this paper in 2014, discovery of the largest historic silicic submarine eruption, because it had a volume greater than the Colombo eruption in the Mediterranean from the 1650 eruption. And based on a ship that went past and did multi-beam bathymetry just after the eruption, we were able to demonstrate very coarsely that there were new eruption products on the seafloor, on the caldera margin, but also within the caldera. So this paper and that initial work that we'd done with that 2012 voyage and the multi-beam system essentially enabled us to put a proposal into the National Science Foundation to use an ROV, Jason. So this is kind of the tool that you use to do field work on the seafloor, has manipulators and cameras and lights and slurpers to suck up biology and ash and that type of thing. And we use the Sentry vehicle, and the Sentry enables us to make really high resolution topographical maps of the seafloor. So this science was done with a whole bunch of US, Japan, US, Japan, UK, Australia, New Zealand scientists. But I just wanted to point out that of the scientific, excuse me, scientific team, half of us were PhD students or undergraduate students. And I think to date, we've published something like 15 or 16 papers since the 2015 voyage. So that's nearly 10 years. And 95% of those are all PhD-led papers. So there's a lesson learned, which I'll talk about at the end of the talk. But anyway, so we got to the top of the volcano, and we just launched this vehicle called Sentry. And so I just thought I'd show a video of how we launched the Sentry. The Sentry is an autonomous vehicle. We program it to essentially mow the lawn and create a graphical map of the seafloor. And so we release it, and it goes and does its thing for about 12 hours until its batteries are almost, and then it comes back to the ocean surface, tells us where it is, and we go and pick it up. So this is a very scary time saying goodbye to the Sentry because it's a $16 million vehicle. Right, but we did it successfully in a very steep caldera type terrain over, I think it was probably 12 different deployments. So on the right-hand side is the map, the ship-based bathymetry map that we had before any of the Sentry surveys. And so you can kind of make out features, like we knew this feature was new, but we didn't know whether it was a lava dome or an explosive cone. We knew some of these little bumps on the southern margin. We knew that there was material in here that was either lavas or mass wasting deposits or something like that. So I'll just show you, So I'll just show you, here it goes. So this is the accumulation of those 12 different Sentry dies and those different maps. And what I've done is I've just overlaid in red those new 2012 eruption features. And so you can just see how remarkable this 1 meter scale resolution bathymetry is. And even without going there, you can tell the morphologies of these features tell us exactly what they are. Like these are lavas that are flowing down the caldera wall into the caldera floor. And these are lava domes with very kind of spiny type tops. So the thing I wanted to point out is that everything that we saw at the surface was a plume and a pumice raft. Because we had the pre-eruption bathymetry and the post-eruption bathymetry, we could tell that there were new seafloor features, which enabled us to get the voyage and the vehicles. But what we found, had we not had the voyage, with the vehicles, we wouldn't have observed 10 intracaldera silicic lavas, which are highlighted here in the red to peach colours, the 4 caldera rim silicic lavas, including this large 250 metre high lava dome, which is about 4 times the height of the Rest Point Casino in Hobart, if you've been there. We wouldn't have seen this caldera wall collapse deposit, and we wouldn't have seen some of the other mass wasting deposits on the caldera walls. And so what looked kind of very simple from satellites was actually not the case, in that this was a very complex and long-lived eruption with a set of diverse eruption, transport and depositional processes. So I just wanted to show you a couple of those, and some fragmental eruption deposits. Yeah, and had this pumice raft not been produced, we wouldn't have discovered this eruption. There was no earthquake indicators to suggest that this volcano had erupted, principally because the nearest seismometers are very far away. Okay, so I just want to show you a couple of things that we learned from this science program. Now, the next shot that I'll show is as if we were standing in this caldera looking up towards this southwestern wall. Yeah. So here is the caldera floor, and the wall in this part of the caldera is about 600 meters high. And what you'll see is this very bumpy terrain. And the very bumpy terrain is on the caldera floor and some of the walls, and then there's a very smooth terrain as well on the walls. So if we just look at what one of these bumps is, we took Oz, and what we found is that the bumps are related to giant pumice glass that are stacked maybe 3 to 4 high on one another. Now, these are absolutely giant. They're slabby, meaning they have very arcuate, planar type features, and they're as big as cars. The largest one that we saw was 9 meters in diameter. So these are absolutely massive. Now, a PhD student from University of Hawaii worked in detail at studying the microtextures, the shapes of these clasts, volatiles present in melt inclusions and also in the glass, the type of traditional things that we would do in for subaerial eruption products, but on these giant pumice clasts. And he also coupled that with some modelling that incorporates things like a reduced amount of volatile exsolution because of the confining pressure of the water, which influences viscosity. Those models also incorporate the limited amount of expansion of supercritical water and or steam at 900 meters below sea level. And that PhD student and Michael Manga and others in 2018 determined that although this magma arrived on the seafloor at Havre at 10 to the 7 kilograms per second, which on land would be a huge eruption with a 20-kilometer high eruption plume, this magma was very, very highly unlikely to have erupted in a gas pyroclast mixture. And so they came up with a model by which you have to pump magma into the ocean at really high eruption rates, and that these slabby clasts are essentially the quench fragmentation of that magma body as it's within the ocean. So this is a very new model and hard to wrap your head around if you're not used to working in submarine settings. The second thing was a PhD student of mine, Fumi Kagami, and he was working on trying to understand if there's any controls on lava morphology when you erupt lavas into the ocean. So water strips heat out of lava much more quickly than it would in air. So we expect higher crust development on lavas. And also these lavas should have more dissolved volatiles in them because of that higher confining pressure. And so what Fumi found was that for rhyolite lavas erupted in Oregon, in Washington, and in Chile, those on land, those have exactly the same morphologies as the ones that he characterized on the seafloor. So there's no obvious role of eruption into water on lava morphology. And so that was kind of interesting for us. That was an interesting outcome. It looks like slope has a much more profound role on lava morphology. Okay, so having all those PhD students involved meant that we actually learned a lot more than what I've been able to present today. So things such as magma storage conditions, and other eruption and transport processes. But our voyage was also able to demonstrate the ecosystem damage to the biological communities that were on the volcano, how the hydrothermal systems were recovering, and principally those two things. So our voyage also delivered some outcomes for marine biologists. Okay, and so just the last example, which is the Bang, which is the Hunga Tonga eruption in 2022. So this is also an incredible eruption that we're still trying to understand, because this eruption took place from a submarine edifice that was partially emergent. And so a lot of the record that helps us understand the eruption drivers, the transport processes, is on the seafloor. Okay, so let's keep going. So this was probably one of the most explosive events of the last century. Huge amounts of energy, sonic boom heard up to 10,000 kilometers away. Unfortunately, there were 3 fatalities in Tonga, driven by the tsunami, and because of the disruption to the undersea seafloor meteor tsunami. It's the first volcanic meteor tsunami that's been observed, and also the devastating tsunami. So there are reports that the tsunami got up to 40 meters in some of the outer Tongan islands, but on the main island, it was generally less than 13 meters in height. So completely devastated all of the infrastructure that support Tonga and housing and things. Okay, so this is what the volcano looked like before 2022. But this edifice largely, this middle part of the edifice largely disappeared in the eruptive activity before the main event. But really, this is the top of a very large stratovolcano. And the stratovolcano has a very large caldera. So this caldera is about 5 kilometers in diameter. So what happened underwater? Well, just like cover, we had the pre-eruption bathymetry of Hunga, and the Korean icebreaker and some teams that used multi-beam systems on fishing vessels was able to kind of do the post-eruption bathymetry. And so I've just got a bit of a video here, courtesy of Carey, that shows the pre-eruption edifice morphology and the post-eruption morphology. So this eruption produced a 850-meter deep hole. About a cubic kilometre of material went into the atmosphere, and most of that's derived from the magma. But there's about 5 cubic kilometres of the volcano missing, and there's also a magmatic component missing that we don't really understand the volume of. So these were the first 2 really geoscience papers that came up. So I just want to talk about these. So the pre and post eruption bathymetry on the left-hand side image was able to demonstrate where there was material, well, new eruption products on the edifice, which is defined by these red zones. So areas of where there's been topographical change and material deposited. And the blue areas are where material has been removed. And so you can see some really amazing features in here. You can see how the top of the edifice has been scoured significantly, especially in the channels that are from the summit into the flanks. You can see out on the distal margins of these channels, there are regions of material being accumulated. You can also see these funny concentric rings, which are sediment accumulation, and we don't understand those yet. And we can also see these kinds of wave-like features of material loss, gain, in the distal part of those channels. So there's a lot of underwater sediment flow dynamics that has taken place that we just don't understand yet. Now, the other paper that came out by Mike Clare and Isabel Yeo in 2024 was using the data provided by the undersea cable companies. So there's a domestic cable that goes past Hunga and goes in this north-south kind of trajectory. Now, when telecommunication cables are disrupted, they know the location where it's disrupted and they know the time. So that's the domestic cable, and this is the international cable. And so with that information from the cable companies and also the timing of the eruptive events at Hunga, as derived by the satellite information, they were able to determine the velocities of underwater sediment flows that destroyed those cables. And so these velocities are in places upwards of 100 kilometres an hour. And so these are some of the fastest sediment flows that have ever been recorded on the seafloor. So that includes mass wasting, shelf collapse and things, just general sedimentary processes. Now, the interesting thing about this international cable was that it was very significantly damaged, but it was actually found 5 kilometres to the north of where it was placed. These sediment flows have picked it up, moved it to the south, and I guess there's been some sort of rebounding process where it's been able to carry the cable into that north position. So these underwater sediment flows have huge eruption-fed sediment flows have huge amounts of energy available. Now, the other exciting thing that was discovered from this event, so I've just got a map from Google Earth here. This is the location of the Hunga volcano, and about 3 to 4 months after this eruption, the ROV Jason was in the Lau Basin to do a repeat survey on some of the hydrothermal vent sites that they've been doing a longitudinal study on. And so when they got there, what they found was not what they were expecting, in that a lot of their sites where they put markers and things were completely covered with ash and products from the Hunger eruption. And so here you can see areas of this Hunger ash and some microbial colonization here. And these areas here, although it's very small, are dead, essentially empty shells from some mollusks. And so even like 80 kilometers away from this volcano, these sediment flows have deposited up to 1 meter of volcanic material. And so this is a really nice study to go back to over the next few decades, just to see how those hydrothermal and biological communities are developing. So in 2025, I'm heading, this is part of my future fellowship research, I'm heading out there with a team of earth scientists, but biologists and marine spatial scientists, to use the Investigator to do a repeat survey of some of the biological communities that were devastated by this eruption. So those biological sites are in the blue circles, and the circle area is essentially the diversity of the invertebrates found in those locations. And we'll also be doing some work trying to understand some post-eruption landslides that have disrupted the domestic cable since the eruption. Now, we also have a fairly ambitious plan to try and understand the volume of the eruption. So that includes the volume of magma and the volume of the edifice. It's really critical that we do this because the eruption volume or the eruption magnitude is so we'll be doing that work too and trying to fill in this isopac map and interpolate volume. There's also another voyage to Hunger Volcano, US-led voyage with Adam, Kristen, Joe and Ryan. And there they'll be using the Sentry to get those really high resolution maps and also the remotely operated vehicles to try and understand these really interesting seafloor features around Hunger. So what did we learn, or what have we learned since? We've learned that it's a high magnitude eruption at approximately 200 meters below sea level, got fast and powerful seafloor sediment flows, and those biological communities were devastated. But there's a lot of eruption unknowns. Until we get onto the seafloor and sample, just like we would in a subaerial setting where we've got our PPE and our boots on and our hand lenses out, until we get on the seafloor to do some sampling with coring and or the ROV JSON, it's going to be really tricky to understand those submarine eruption transport dynamics, the conditions of how this eruption was so powerful for an andesite volcano, an andesite magma, and those sediment flow dynamics. And we also want to do a little bit of work to understand earthquake-triggered landslides that have affected the domestic cable and the susceptibility for more of that landslide activity and disruptions to Tonga communications. Okay, so that's the end. And I just want to have a couple of slides about working in the marine geosciences. So the thing that I absolutely love about working in underwater in the marine realm is just the team-based science, in that typically it's a very multidisciplinary group and you're at sea together. And if you're the chief scientist, you're lucky enough to put people on the voyage who you can work with and who you have a really good time with. And so usually these ship-based voyages are really, really fun and such an enormous opportunity for PhD students and postdocs to just learn multidisciplinary science. The second thing about team-based marine science is that there's lots of opportunity for outreach with younger kids. So, for example, taking these styrofoam cups down to a kilometre ocean depth and the cups that kids have decorated and then giving them back after the voyage, but also eating lots of ice creams and eating lots of Easter eggs. So that's also a fun bit of marine science. But there's also some challenges around working in marine science, and it's probably not just marine sciences, it's probably Antarctic science as well. And that is the significant time investment you need to make in order to do these multi-million-dollar, multi-month programs of field-based research. So these areas are typically remote, and so there's a lot of work that you need to do with the Marine National Facility, for example, or some of the international equivalents. So what I did was I just mapped out how much time I've spent in terms of writing the voyage proposal, which was about 16 days through March to May. Then when the voyage was funded in January, but I didn't really have to do anything until August. And so that's when we got the voyage manager. And that's when the voyage manager puts in place some timelines for you to be planning operations, equipment lists, what equipment you need, can it be integrated into the ship? And then if you've invited personnel from other institutes, you need to also find their salary contribution for their time at sea. And so this is kind of the time that I've spent already in August, September, October. So anywhere between 1 day a week to 2 days a week. In November, I'm expecting to use my 2 days a week to prepare the voyage plan and also try and understand what equipment we're bringing on the voyage. In December, it'll probably be the same. Now, early next year, it drops off, but it really ramps up in July as we're planning for the voyage itself. And then after the voyage, there's a lot of voyage reporting, there's a lot of sample curation and sending samples to different groups. And then in 2026, I'm expecting to do a lot of project management. And so I calculated this. And over that 3-year period, I'm going to be spending 161 days of my 312 research day allocations. So there's just a bit of, that was actually a surprising number for me. And it's just highlighting the time investment you need. And so it's kind of highlighted to me that as an early career researcher, it's really difficult to take on a chief scientist role in a voyage like this because it takes away from some of the other performance indicators that you need to be competitive in terms of ARC type grants and or proposals. There's also some other challenges of marine Antarctic science. So financial constraints. So I'll be away for about 8 weeks. We'll need extra childcare. My husband will have to take leave without pay. This is something I'm struggling with at the moment, the emotional impacts on families. So I don't really want to be away from my family for 8 weeks. And there's probably, as this graph indicates, there seems to be a disproportionate effect on female scientists. So this is the percentage of female chief scientists on voyage across these different oceanographic institutes with time. And you can see that of all the chief scientists, of all the voyages that have chief scientists, only 25% or so of those are female. So yeah, disproportionate effect on female scientists. There's probably a number of reasons for that, some of which I've highlighted, but potentially also some of the experiences that females have had on ships and in Antarctica and other environments like that, where there's been instances of sexual harassment and sexual assault. Yeah. So this for me has triggered a lot of thinking. It's something that I'm thinking about in the next few months about collecting some data from the Australian system and plotting that up similarly. Okay, so I just want to finish there, but I also just want to say another big thank you to the WMESA committee and also the past speakers of WMESA.
Thank you so much, Rebecca. That was fantastic. We've got a few minutes for questions. If anyone has any questions for Rebecca, feel free to unmute yourself and sing out, or you can pop them in the chat as well. That was, yeah, I found that really, really interesting. I have a quick question to start off. Have there been any comparisons or evaluations done on what the scale of the eruption would have been for the Tonga Hana, I think it was, eruption, if it had been subaerial rather than underwater? Because it was a monster, right?
Yeah, so interestingly enough, the day before the eruption, the big eruption, there'd been an eruption column height that got to 20 kilometres, but it was very short-lived. These andesite stratovolcanoes typically do have explosive eruptions with plumes at that height, but for andesite magma to be so explosive is highly unusual. Yeah. And so there has to be an external trigger, and whether that's water or magmatic gas involvement or storage involvement is an outstanding but really exciting question.
Amazing. Thanks, Rebecca. Marissa, go for it.
Hi everyone, and thank you so much, Rebecca. That was wonderful. I'm here with my student Wee, and Wee's working on some ancient volcanic deposits from the Cambrian. Um, I was really interested when you were talking about the ash, and I'm a paleontologist, by the way, so I was very interested when you talked about the ash just blanketing those deep sea communities. But it made me wonder if there's what about the microfacies or textural differences between ashes that are deposited like that in a marine realm versus ashes that are deposited in a terrestrial realm? Can you kind of distinguish them based on like small scale microscopic features?
Yeah, there's a student at the moment, Marcus, who is about to publish his paper, and the thing that they did with that ROV voyage was that they so that ROV voyage to see the hydrothermal vents was a boat full of microbiologists, hydrothermal geologists, and Marcus was only a master's student. He was a sedimentologist. He never worked in volcanic terrains, and suddenly he was the expert because he was the geoscientist on the voyage. And so he emailed a few of us and said, "Look at this. What do I do?" And based on what was on the ship, they were able to core those deposits. And Marcus' paper should be published imminently, but in his papers, he was able to define turbidite facies. So there's some lateral transport of that material from hunger, and then a suspension fallout facies, which is just the very fine material sedimenting out of the water column. So he was able to identify that in that very distal location.
What about like glass shards and bubble shards and stuff like that? Do you still get those sorts of things?
Yeah, if the magma is essentially a magma foam, like a very porous magma
Right.
foam when it's fragmented, then yes, you'll see the interstices between the bubbles, which are these
Yeah.
bubble shards.
Yeah.
But it's not yet been demonstrated as far as I know, that magma that erupted at Hunger was really vesicular.
Right.
Yeah, so you might not see the bubble wall shards for this deposit. I'm not quite sure.
Mm. Yeah, because it seems to be, that sometimes when we look at our materials that there are some 100% that you get the bubble shards and the bubbles and things like that. But then I imagine as well in a marine realm that there would be lots of opportunities for these materials to be kind of winnowed and separated or moved around by density and
Yeah.
reorganized and
Um,
mixed with other sediments as well.
yeah, sure. I've got a student, Malai, who's working in the Macquarie Arc on some of those Cambrian to Ordovician rocks. I'm actually at North Parks right now.
Oh, really?
And yeah, here I
Cool.
am. And Malai has one facies where he's sure that he's got bubble wall shards. I think they are bubble wall shards, and I think last week we convinced Ray Kaz that they were bubble wall shards. So
Okay.
they can survive.
Yeah, okay. Well, maybe I'll get in touch with you. Thank you, Rebecca.
No worries, Marissa.
Awesome. We probably have time for one more quick question if there is one, and then we might take a quick break just so everyone can grab a fresh cup of tea, nip to the bathroom if they need to before we start the AGM. Teresa, hello.
Hello, Rebecca. That was a great talk. Thank you so much. It was fantastic. I really enjoyed it. I'm gonna piggyback on that question about Tonga and about the extreme event it was. And you mentioned that the gas content was a bit unusual, generating global warming, a little bit of warming. Do you think that has something to do with the oddity of this eruption and its massive explosivity, or what do you think? I know you don't know yet, but what's your guess or your hypothesis?
Yeah. So interestingly, the first few papers that came out about this eruption were written by folks from NASA and other folks who work with the satellite sensors. And so with those satellite sensors, they're able to determine things like the amount of water, the amount of sulfur in the eruption plume. And so some of the earliest papers demonstrated that the eruption plume had very little sulfur. I can't give you any numbers, sorry, and high water contents. And so I think that the global warming event, I think the ratio of the lack of sulfur, well, the sort of a competition there, but the ratio between not having the sulfur and having this huge amount of water, I think the end result was that the water, the higher amounts of water should have much more effect on global warming than the lack of sulfur. Yeah, I think it was a very transient global warming event. Like I think it was over within a few weeks. Yeah, so it got back to equilibrium quickly.
Thanks. Thanks again. It was great.
Brilliant.
Yeah, thanks, Fraser.
Thanks so much, Rebecca, again, for taking the time to speak to us all today. It was really fantastic. It was really amazing to see how multidisciplinary the work is, and just the insights into, the challenges that scientists in the field are facing, particularly female scientists. So thank you so much for sharing.